So here we are now with limits at infinity, and that specifically means that we're going to talk about when x approaches infinity. And there's going to be a basic set of equations here that we're really going to boil everything down to that gives us our answers. And I want to start with 1 over x. Now, if you look at this function, as x goes to infinity, that this function approaches 0. And if you look to the left, as it goes to negative infinity, the function also is approaching 0. And this is also true for 1 over x squared, 1 over x cubed, 1 over x fourth, and so on. In all these cases, the limit as x goes to plus or minus infinity is 0. And we're going to use this to solve most of our limits at infinity. In other words, we're going to try to get to a position where we have something like this, and then we will know that limit is 0. And I want to start with just some examples of that. So let's say we have this limit here. The first thing we can do is use some limit properties on this because we know the limit distributes. And so we can have it equal that. Now we also know that constants we can pull outside the limit. And here now is our limit of 1 over x. This function right here. And as x goes to infinity, this limit will be 0. And the limit of a constant is always that constant. And there's our answer. So this limit equals minus 1. Let's check out another one. And again, just using these functions on the right here. And again, this does extend for all positive integers. So 5, 6, 7, 8, and so forth. Let's check out another one. Now with this limit, now we have our 1 over x sitting in the denominator here. And again, we can use limit properties here. Remember, the limit has this unusual property of passing along to the numerator and the denominator. And so we can pull off that maneuver. I'm just going to move this down and over here. And the limit of a constant is always that constant. And in the denominator, the limit distributes. And again, the limit of a constant is always that constant. And here we are. The limit of 1 over x, this function here, as x goes to infinity. And here's that limit, which we then know is 0. And so our final answer is 1/2. So not too bad there, hopefully. Let's check out a trig function now, because there's something I do have to say about sine and cosine. Now, this is only true for sine and cosine, what I'm about to say. So now we're going to take the limit as x goes to infinity, and we have a trig function here. And what happens to sine as x goes to infinity? Well, it oscillates forever. In other words, it doesn't converge to any value. Sine is going to be bouncing around between -1 and 1 forever and ever as x goes to infinity. It's going to bounce and bounce between that. It's never going to converge to a single value. And so as x goes to infinity, we know sine of x is going to be some number that's always between -1 and 1. Now, I'm going to be probably a lot loose with math notation here, but this is the point of this is to express an idea, though. So sine of x, as we go to infinity, this function is going to be oscillating between -1 and 1. And this is always going to be just some constant. It's just some number. So I'm just going to pull us outside the limit. And we have this scenario. Oops, there we go. It looks a little better. And so we have our limit again of 1 over x. And that goes to 0. Now, I do want to say again, I am being pretty loose with math notation here. I'm trying to express this idea that sine of x bounces around between -1 and 1. It's not going to blow up to infinity, which is the main point here. Sine of x will always be some finite number. It's not going to blow up to infinity. And then the limit of 1 over x does go to 0. So we have a case where we're going to have 0 times some number from sine, and that will always be 0. And that's our limit. And this is also true with cosine. Cosine bounces around between -1 and 1 as x goes to infinity. And the important point there is that it does not blow up to infinity. The cosine function does not output larger and larger numbers to infinity. It's constrained between -1 and 1. And so as x gets larger and larger and larger, 1 divided by a larger and larger number is going to infinity, whether that's -1 or 1. So that was some problems just using the 1 over x over here. But there's something else that is also very useful, and that is dominant terms. And to talk about dominant terms, here is a graph of x. That's what it looks like. And here is x squared. Now remember, x is going to be going towards infinity. So these numbers are going to get absurdly large. And look how fast x squared is already moving away from x. Even at an input of 2, x is already doubling the output of x here. X squared is doubling the output. Imagine then if this was 2 quadrillion, then x squared would dominate x. X squared would be outputting such a large number at 2 quadrillion that the effects of x would be insignificant. And we would say x squared then is dominating x. And when we mean by dominate in math, we're saying that everything else is not contributing in a significant way. And this hierarchy continues because x cubed outputs even faster than x squared. And x to the 4th outputs larger numbers even faster. And so on. This hierarchy continues. And so as numbers get absurdly large, which which is what we mean when x goes to infinity, we're talking about absurdly large numbers, then the term with the highest power will dominate. It will simply crush all the outputs of everything else and say, you're just nothing. All that matters is what I'm outputting now. And I want to show you in mathematically, or algebraically at least, a way that I could also show that. So let's say we have x to the fourth plus x to the third. We have this function here. And I'm going to write it in a way that may seem unusual, but I'm going to write it like this. Because x times x cubed is x to the fourth. So as x gets larger and larger, look how much larger x to the fourth gets compared to x cubed, the next highest power. So if x is 1,000,000, x to the fourth, because of this x right here, x times x cubed, x to the fourth is already 1,000,000 times larger than x cubed. If x is a quadrillion, then x to the fourth is a quadrillion times larger than x cubed. And this is what we mean by dominate. We literally mean it crushes everything. X cubed becomes insignificant at large numbers compared to x to the fourth. And so taking a very simple limit here of x to the fourth plus x cubed, what I'm saying here then is that as x goes to infinity, this x to the cubed just doesn't matter anymore. It's just dominated by x to the fourth. It becomes insignificant. So let me show you something that has a little bit more meat and potatoes to it. There's some more full-blown polynomials. Let's take a look at this. So we have x going to infinity. And what we want to look for here are dominant terms then, in the numerator and the denominator. So if we look at the numerator here, x to the fifth is just going to crush everything out of existence. Well, not out of existence, but to being absolutely negligible. And so we're just going to get rid of it. X to the fourth is going to crush minus 5x. And so we get rid of it. And now we can do some simplifying on this. So 3/7, that's a constant. So we can pull that outside the limit. And x to the fifth divided by x to the fourth is x. And what is the limit of x as x goes to infinity? Well, that's the red line here in the graph. Well, that does go to infinity. Now, the answers in this section of the homework are going to want infinity for these answers. I made a mistake there and got rid of this equation. I just want to put it back again. So that's where we started. And then here's after where we ended up. So the first step was dominant terms. We got rid of everything that wasn't dominant. And then we did the limit. Now notice in this case, the dominant term was in the numerator, x to the fifth. The dominant term is the term with the highest power. So 5, the largest power here. So 5, the dominant term, was in the numerator. So let's check out. By the way, you may have seen this in algebra. Some teachers do talk about this with horizontal asymptotes. You may have learned 3 rules. You may have not known where those rules came from, but you may have learned them. They come from the limit. So let's take a look at this one. And we're going to get rid of everything that's not dominant. So the dominant term is the highest power, so we'll get rid of the minus 5x. The dominant term here is x to the fifth. We'll get rid of everything here. And so that's our dominant terms maneuver. So let's do some simplifying on that. So the 7/3, that's a constant. We pull that outside the limit. And x to the fourth, x to the fifth will reduce to 1 over x. And 1 over x, well, that's from then back to these functions. We know the limit of 1 over x as x goes to infinity is 0. And then 0 times 7/3 will get us 0. And that's our limit. Now what's happened, there is a pattern emerging here. Again, if you did hear about these rules in algebra, if the dominant term is in the numerator, this limit will always go to infinity. Dominant term in the numerator, that limit is always infinity. If the dominant term is in the denominator, that limit is always 0. And so what's the last case? Well, the last case is when both the numerator and denominator have the same dominant term. Like this example. So now if you look at this, and we make our dominant terms maneuver here, well, we'll get rid of everything that's not dominant. So we'll get rid of the minus 5x, get rid of everything here, it's not x to the fourth. And there's our dominant terms maneuver there. And then we can simplify. So 7/2, a constant we can pull outside the limit. And then x to the fourth divided by x to the fourth is 1. And what you should burn into your brain? The limit of a constant is always and so that's 7/2. And these are the three outcomes. So looking to the right here, if the dominant term is in the numerator, which was the first problem we did, right here, then the limit goes to infinity. And it can be that simple. You can identify the dominant term in the numerator, you're done. In the second case, if the dominant term is in the denominator, then that limit goes to 0. So there it is, x to the fifth in the denominator, and that limit goes to 0. And in the third case, if the dominant term is in the numerator and denominator, then the limit goes to the ratio of the dominant term's coefficients. So look back at the original equation. The dominant term, x to the fourth, had coefficient 7. The other dominant term had coefficient 2. And this limit will always be that ratio of those coefficients. So these are the three outcomes. Comes from the limit doing that. And there's nothing wrong with memorizing these three outcomes so you can identify it and get your answer quickly. However, I do think it's still very important that you can actually do this through the limit, though. So let's check out, then, something that has a trig function in it. How about this example? So first off, this sign is going to oscillate between some number, it's going to be some number between -1 and 1. And again, the point here with sine and cosine is that they do not blow up to infinity. So something I could say here is I could call this A and B. These are going to be some numbers that do not blow up to infinity as x goes to infinity. That's the important thing to understand about sine and cosine. Now, the other trig functions do have points where they blow up to infinity. So you're only going to see sine and cosine in these homework problems because of that. But A and B, these are some numbers that are between -1 and 1. So what's our dominant term here? Well, remember, A, the largest A can be is 1, because that's the largest a sine function can output. Whereas x, as x goes to infinity, x could become quadrillion. Now, quadrillion plus 1, is that significant? Not at all. As x goes to infinity, minus x here will crush sine into being negligible. And same with cosine. As x goes to infinity, so think of x being a quadrillion. Well, a quadrillion plus 1, insignificant, gone. And same with 2. What 2 and quadrillion? 2 is insignificant. Again, the dominant terms are the ones with the highest exponent. And notice here, the highest exponent here with x was 1. And so that's our dominant terms maneuver. All that's left are the dominant terms. And this simplifies minus x divided by x to -1. And now this is a point where I wish we were all in class, because this is where I would say, let's say it all together. The limit of a constant is always that constant. And that's our answer. So let's try another one that looks a little bit more intimidating. And how about this limit? So, dominant terms in the numerator and the denominator. So if we look at the numerator right here, x cubed will crush 1. And x squared is going to crush 7x as x goes to minus infinity. And now all we have left are the dominant terms. And x cubed divided by x squared is x. And there is still a minus sign here. And then finally, minus to the 5th power will give us a minus again, and then x to the 5th. And the minus is a constant, so we can pull that outside the limit. And we really don't need to use parentheses anymore. And as x goes to infinity, what's going to happen here? Well, x to the 5th is just going to go to infinity even faster. Now, if we ignore the minus sign for a moment, minus numbers to the 5th will output minus numbers. So this limit is going to minus infinity. However, it is being multiplied by a minus sign, so this is going to positive infinity. And that's our answer. And again, notice the dominant term is in the numerator here. Now the question I'd be interested to hear your answer is, what is the dominant term in the numerator? Is the dominant term x cubed? Because the dominant term in the numerator is technically x to the 15th. And in the denominator, the dominant term here is x to the 10th. And that will matter. And I will show you an example. But let's check out another one that looks even scarier. And I think what scares some people about this is that -1 hanging there. So dominant terms. So square root. Recall the square root means power half. And let me just leave it. And x to the -1. Remember, if we want to change the sign of an exponent, then we put it across the division bar. So if I want to change this -1 to a +1, then I need to take x across the division bar. And that'll make its exponent positive then. So in the numerator, dominant terms here, 3x will crush -7 as x goes to infinity. Now as x goes to infinity, what happens to 1 over x? Do you remember from the start of the lecture? As x goes to infinity, 1 over x goes to 0. And that will certainly be crushed by square root of x. So there's our dominant terms. These constants, we can pull outside the limit. And now we can make a simplification. That x to the 1/2 divided by x means 1 over x to a half. So we have the limit of 1 over a number that's getting larger and larger. So we have like 1 divided by a billion, 1 divided by a quadrillion, 1 divided by a Google, 1 divided by a Googleplex. This limit is going to 0. 1 divided by a number getting forever larger without bound is a number that's going to 0. And then so 0 times 2/3 is 0. And as a last one, I like this one because it's tricky. Got to pay attention to detail here. Because at first glance, you may see this x to the 6th down here and go, oh, the dominant term is in the denominator. And then you might go to your rules over here and say, oh, if the dominant term is in the denominator, then this limit goes to 0. And bang, you might be done and say, hey, that's 0, I'm good. But what I like about this one is the square root. Because the square root, you can't ignore. So let's check this out. Dominant terms. If we look at the numerator, x cubed will absolutely crush 4. And if we look at the denominator, x to the 6 will absolutely crush 9 as x goes to -infinity. And so there's our dominant terms maneuver. And now the square root comes into play. Remember, the square root means power of half. And when you have an exponent raised to an exponent, it means you multiply. So 6 times a half, the square root of x to the 6 is x cubed. In other words, the dominant term in the denominator is not x to the 6. The dominant term in the denominator is x cubed. And now you can see these x cubes cancel. And the limit of a constant is always that constant. So that's why I like this one. And like it, I mean for kind of testing reasons. Hint, hint. Because I think this is a good test. Now, it is a little bit more challenging. Don't get me wrong. There's going to be easy problems on a test as well as more challenging ones. But I like this one because it's got a little bit more attention to detail to it. You may be tempted to go right with the x to 6 and say, oh, well, this is going to be 0. But upon further inspection, if you look at the square root, you see it's actually x cubed. And this is a case of actually the third, where the dominant term is in the numerator and denominator. And so our answer was the ratio of the dominant term coefficients, which was then -3. And I do want to say one last thing about dominant terms, is I am only talking about x going towards infinity. So there are other ways to talk about dominant terms. For instance, if we had, let me just rewrite this really quick. We had, say, 1 over, be something like this, as x goes to 0. If we look at this, now I've made x go to 0, which is something completely different. The dominant term in this case would actually be 1 over x cubed. Because as x goes to 0, it's 1 over x cubed that's now blowing up to infinity. And so dominant term, what we really mean in general, is that this is the term that is controlling the behavior. So there are other ways to have dominant terms. For us, though, we're specifically talking about x going to infinity, and that does mean the dominant term will always be the one with the highest power. And actually, there is one more last thing that I want to mention, and I'm just going to scroll up here to pull up a function for example. Here's a, let's pick this one. Is the book mentions a way that I was also taught how to do this when I first learned this, and I'm just not a fan of this method anymore. I think the dominant terms is a more intuitive way to handle this. But what the book stresses, as you read along there, which you should be doing, is that they will say divide everything by the highest power in the denominator. And so I just want to mention this quick because I don't want to totally ignore this part here. So the book is saying take the highest power in the denominator, in that case that's x to the 5th, and divide everything by it. So if we divide x to the 4th by x to the 5th, then that's going to mean 7 over x. If we divide x by x to the 5th, that means we'll have an x to the 4th then in the denominator there. And x to the 5th divided by x to the 5th is 1. X to the 4th divided by x to the 5th would get an x in the denominator there. X cubed divided by x to the 5th, 1 over x squared. And 1 divided by x to the 5th is 1 over x to the 5th. And why would you do this? Well, because the limit can pass along to the numerator and the denominator. And then once we do that, we can distribute the limit to each term then. So here I used the limit property to pass the limit along to the numerator and the denominator, and then the limit will distribute to each of these terms. And now these limits go back to the 1 over x, that these limits go to 0. So we know this will go to 0, and this will go to 0, so the whole numerator goes to 0. And if we look at the denominator, as x goes to infinity, a constant stays a constant. But all these others will go to 0 as x goes to infinity. And so we get 0 over 3, which is 0, which is the answer we had before with dominant terms. I think both these strategies will get you the same answer. And so the book does put an emphasis on this approach, which is the approach I was also taught as well when I first learned this. And there's nothing wrong with it. I just don't think it's quite intuitive as dominant terms. And dominant terms, I think, are overall just a more useful thing to get accustomed to. So if you want to do it this way, there's nothing wrong with that. I'm not going to tell you how to do it, as long as you do it correctly, and there you go. So nothing wrong if you want to do it that way. I do encourage you, though, to start thinking about dominant terms, because there's many reasons into a math future while your ability to recognize dominant terms can be helpful. And there is limits as x goes to infinity.